Okay, our next speaker is Yasin Simsek from Duke University, who's going to talk about intraday variations in systematic risks and information flows. You have 20 minutes, Yasin.
Yeah, thank you. Thank you for having me today. This is a joint work with Andrew Patton from Duke University as well. So, okay. So the factor models in asset pricing literature is very common, and it's a fundamental tool for understanding risks in asset pricing. So a typical factor model is we have returns at the left-hand side, and we have factor exposures, beta, and the factors, and the plus the residuals at the right-hand side. So the most common approach for those factor models is using some observable factors. For example, the CAPM, the capital asset pricing model using the market factor, or the extensions like FOMO-French 1993 or the other FOMO-French 2015. They are using size, value, or momentum factors. So later, those kind of observable factors called factors by Cochrane in 2011 Journal of Finance paper. So an alternative to using those pre-specified set of factors is using the unobservable factors. So basically, the idea is that estimating those factors directly from the data, commonly using the principal component analysis. Typical examples is the Connor and Koratzik in 1986, and recently some researchers proposed new version of this principal component analysis, like the instrumental PCA by Kelly et al. Or the risk premium PCA by Letau and Pelger in 2020 RFS paper. They also, this PCA also recently applied to high frequency returns by Pelger Journal of Finance paper. So the standard implementation of those factor models, the observable factor models and the latent factor models, assume that those factor exposures, the beta, are fixed over the time. But we know that, and we have strong evidence for the time varying volatility, the time varying correlation, and the time varying risk premium. So these evidence can motivate the time variation in factor exposures. So in the literature, the time varying factor exposures have already studied a lot. For example, the Connor et al. 2012 and Gagliardini 2016 Econometrica paper, and again the Kelly 2019, they have all proposing some sort of time variation in beta, the factor exposures. Mostly they use some sort of functional forms that links between the factor exposures and some market variables, or like economy-wide variables like VIX, or some sort of like the interest rates, for example. So for these papers, and these papers consider that variation at lower frequencies like daily and the monthly level. So a recent empirical evidence showed that those factor exposures can vary also within a trading day. So the recent papers by Anderson et al. 2021 Quantitative Economics and 2023 Journal of Econometrics paper find that the factor exposures, so in fact, the market beta and the market beta can vary systematically over the trading day. So also the recent working paper by Liao and Todorov, they also show that the span of factor exposures estimated from the PCA can differ at the market open and the market close. They define the market open as the first 2 hours and the market close as the last 2 hours. So motivated by this empirical evidence, in this paper we propose a new framework to allow for intraday variation in latent factor models. So to do so, we combine the principal component analysis with the non-parametric kernel methods. So the resulting model is kind of generalized the standard PCA of Connor and Koratzik in 1986 Journal of Financial Economics paper, and we call this new framework as the intraday PCA. So let me summarize our main findings. So we apply this new framework to the US stocks. from 1996 to end of the 2020, and we show that it has superior exponential power relative to well-known models in the literature. We also have a stylized model of asset pricing and the information flow, which kind of reflects the empirical results that we have in the first empirical exercise. Third, we also investigate our model, so how our model behave in three different empirical exercises. So basically, we evaluate our model in earning announcement days, the FOMC announcement days, and the other overnight information flows days. And at the end, we will argue that the information flows can lead to these intraday variation. So this is the outline of this presentation. I will first define the local PCA for the high frequency asset returns. Since we have very limited time, I will skip the stylized model for information flows and factor structures. If time allows, I will show some results from this section. So how this information flow can change these factor structures, or can introduce some variation in factor exposures, let's say. So this paper, relates to different part of the literature. So in terms of methodology, we are related to the principal component analysis for economic data papers like the Chamberlain, Rothschild, Conrad, Korosdik. These are the first papers that applies PCA to the financial data. And also Stokan, Watson, and Bayenge are very famous with this principal component analysis and the latent factors in macroeconomic data. There is also recently become popular the literature high frequency factor models. There are good papers, like our paper is most related to the Pelger 2010 Journal of Finance paper. They apply this PCA directly to the high frequency data. They look for the continuous covariance matrix of continuous returns and the jump returns different, and so on and so forth. We also relate this paper to the information flow and asset prices to explain to empirical findings that we find with a new framework. So let me define the PCA for the asset returns. So I will start with the notation first. These are IT minus 1 plus tau indicates the return on asset I observed at day T and the intraday period tau. So bold R T minus 1 plus tau is the n by 1 vector of returns of all n assets at that time. So this capital bold R is T times n by n matrix of returns on all assets and across all time periods. So basically we have T days, m intraday periods, and n assets in the model. So we assume that the returns follow an approximate factor structure. So we have the cap R at the left-hand side, which is a very big panel, T times n by n, and we have factors, which is F, and the exposures, which is capital and bold B, and the plus the residuals. Also, we assume that we have capital K factors. So for now, I will assume that K is known. Then in the empirical section, I will show that how I estimate the number of factors. So in PCA, we estimate the factors and exposure at the same time using these least square type of optimization problem. We solve this problem subject to orthogonality restriction to identify the factors and exposures at the same time. I assume that these factor exposures are orthogonal to each other. So this problem can be easily solved by computer programs. This beta hat, the exposures is just the first k eigenvectors of this covariance matrix associated with the k largest eigenvalues. So it's So computationally, it is easy and the fast. The program languages have fast functions to solve this problem. So once you get the factor exposures, you can estimate the factors by just regressing the returns on the exposures. This is just basic least square regression. Then also you can have the predicted returns by multiplying factors with the exposures. So in summary, once you have the factor exposures, you have the everything, the factors and the return predictions and so on and so forth. So the idea for the local PCA for the high frequency asset returns is as follows. So rather than applying the PCA to the all days and all intraday periods, we can consider this PCA for each intraday period separately. So basically consider the tau, which represents the intraday period. We can estimate the factors, or we can estimate these factor exposures separately for each intraday period, and we have m intraday period in this model. So since we have PCA estimation procedure, which is very fast, so this problem also can be solved by the same estimation strategy in a fast manner. So however, the adjacent periods through the day could be similar to each other. So that means we can draw some information from neighbor periods. So that could improve the accuracy by using some information from the neighboring periods. So that idea motivates the combining the PCA with the non-parametric kernel estimation. So basically, we will have a kernel over the intraday so that we can optimally draw some information from the neighboring intraday periods. To do so, we now add a kernel. So introduce a kernel to the estimation problem. So this phi is a kernel function and the h is the bandwidth. And this tau is the target, our target intraday period, or let's say, I mean, our interest. I mean, we interested in the factor exposures at intraday period tau. So, and the idea of this local PCA is the solving this problem for each tau. So of course, the kernel downweights the other periods that are far from the target period tau. So, and so with a, I mean, little algebraic manipulations, you can show that this is equivalent to standard PCA on the weighted returns. So, and it becomes, you know, easy to solve, and then the computations are fast. So, but now we have to choose a kernel and deal with the bandwidth cross-validation. So for this paper, we consider the familiar Gaussian kernel for the local PCA estimation. The form of Gaussian kernel is as in the slide. So we also truncate this kernel so that the 9:30 a.m., I mean the market open, is not treated as adjacent to the market close. Yeah. So the bandwidth parameter controls how much information we draw from the neighboring periods. So if h goes to infinity, then we end up with the classic PCA that we have, you know, just flat weights, and we treat all the periods jointly. If h goes to 0, then it becomes like period by period in PCA. So our framework is positioned in the middle ground of these two extreme cases. So, and we will select this the optimal h using a validation sample. So let me show the shape of kernel function. So I plot this kernel function using the bandwidth parameter that I validate in the empirical section. So for example, this blue line is the kernel function for the 945. As you see, for the 945, after 1 p.m., we have very low weights. We don't, I mean, optimally, we don't put any weight after 1 p.m. returns. And the same for Same for the green, and for the green for the 4 p.m. and the orange one is the noon time, and it has like more weights on the market open and the market close comparing to other cases. So let me introduce the data. So we study every stock that was ever listed on the S&P 500 index between January 1996 and December 2020, and which traded for the full sample period to have a balanced panel. We have 407 stocks, and we have more than 6,000 days. We drop, by the way, the days with the incomplete trading hours. So, and of course, the data source is the New York Stock Exchange tag database. So we consider 15-minute returns, and we drop the overnight period. So we only focus on the intraday periods in this paper, and that means we have 26 observations per day. So let me explain the estimation strategy that we use. So we use 1-year windows of data for training, validation, and the testing. So basically, we estimate the models across a range of hyperparameters. So we have only one hyperparameter in this case. We just have bandwidth. For example, using 1996 data. Then we select the optimal hyperparameters using 1997. This is typo, I'm sorry for that. So then we compare the models using 1998. So then we repeat this step on the next block of data for the 1997, 1998, and 1990. So these three block scheme is just rolling over the sample period. So we consider a range of factor models. So intraday PCA is what we propose in this paper. So we have also 4 different benchmarks, which is standard PCA, very similar to Pelgrim's 2020. Of course, we have the CAPM, Fama-French 3, and the Fama-French 6, which is Fama-French 2015 plus the momentum factor. So these are pretty standard benchmarks in the literature. So we compare and evaluate the models using the total R square, which is introduced, which is also studied in similar papers by Kelly and the Jew 2021 papers. So we also assess the improvements in the fit using the Diebold-Mariano test, which is, the panel robust version of the Diebold-Mariano test. So critical ingredient in the latent factor models is the number of number of factors. So we adopt a widely used information criteria proposed by Bayan Ench 2002 Econometrica paper, and this is recently extended for use on high frequency data by Liao and Todorov 2023. So basically, the estimated number of factors is the sum of this is unexplained log of unexplained variation plus some penalty. So in this case, the lambdas, the lambda 1 to lambda n denote the sorted eigenvalues of these covariance matrix. So for the standard PCA, we allow this k hat, the number of factors, to vary each year. So we estimate the models using each year data. So for the standard PCA, we allow this to vary each year. But for the intraday PCA, we emphasize the intraday variation in the second moments of the returns. And to do that, we additionally allow to vary across the intraday period. So we might have, let's say, 5 factors at the market open and the 3 factors at the market close. That depends on this information criteria. So this is for the number of factors for the standard PCA. So basically, we start with the 1 factor in the sample, then we go for like 4 factors at 2020 and 3 factors for the 2019. So it's kind of upward sloping in our sample. So this picture shows the number of factors estimated for the intraday PCA for each year and for each intraday period. For the visual clarity, I just create some year groups. and show the median value of each estimated number of factors. For example, the blue line here shows the number of factors estimates between 1996 to 2003 in each intraday period. For example, we start with the 2-factor and at the end we have just 1 factor. So this red line, for example, represents the end of the sample, end third of the sample. And we have, for example, 5 factors at the market open and the 3 factors at the market close. So this table shows the R-square results for the different factor models. So the first row here is the R-squares in terms of percentages, and the numbers in the parentheses are the Diebold-Mariano tests. And we always test with the benchmark versus the intraday PCA, what we propose. And the positive Diebold-Mariano test indicates that the intraday PCA, what we propose is beating the factor model, the baseline, the benchmark factor model. So the first result is that the intraday PCA have superior performance comparing to both observable factor models and the latent factor models and standard PCA. So the difference between the CAPM and the intraday PCA is 9%, and the Fomafrench 6 model is 5%. So as you see, the standard PCA is the leading competitor in the set of competing models, but it's beaten by intraday PCA, and we have the t-statistics 14.65, which is the strong evidence that factor structure of asset returns changes over the trade day. So if this is not the case, we would expect that the intraday PCA and the standard PCA show similar performance in this out of sample. So the next step is that.
So Yasin, I think it's time to move on to the conclusion. Yeah.
Okay. Okay. This is the let's say this is the final slide then. Okay. So this paper emphasized this intraday variation a lot, and we also show the R-square differences between standard PCA and our intraday PCA over the trade day. So basically, what we find is that this difference, this 1.8% difference, is mostly coming from the market open. So we have like 2.5% improvement at the market open, and these are significant. But at the market close, we have so very small improvements, and these are mostly insignificant, as you see. So based on this picture, our paper argue that this wedge between market open and market close could be caused by the information flows during the overnight or at the middle of the day, so that something changes in the stock market and we see this intraday variation. And the rest of paper is kind of elaborating on this idea. Okay, and I am done.
Thank you very much, Yasin. That was wonderful. Let me stop the recording.